Good afternoon, ladies and gentlemen. It's our pleasure to welcome you all to our events for offshore and wind energy, a vision for the future. It's the talk and the presentation will be conducted by Professor Feargal Brennan, who we know, or I know from his talk that he gave to ASME, engineer for mechanical engineers. And it was an excellent talk. So I contacted him and on the behalf of Al-Kindi Society to give talk to our community and society and the subject of wind energy. Kindly he accepted, and it's a pleasure for me to introduce him. But first, if I may give you brief about Professor Feargal. Professor Feargal is Professor of Offshore Engineering and Head of Naval Architecture, Ocean and Marine Engineering Department in the University of Strathclyde and Director of University Offshore Engineering Institute. He is a world-leading expert in resilient engineering and structural integrity, particularly applied to ship and offshore structure. I can go on, but I'll jump because his career is full of activities. But I can go on and say has been the author of a number of reports for the UK HSE. But also he is the UK standing member and leader of the UK delegation to the ISSC, the International Ship and Offshore Structure Congress. He has served as an expert witness in the London Court of International Arbitration. I can go that he got many funds and research and initiatives, but that means I'll talk more from his time and his interesting talk, which I'm not intending to do. To be honest, I would like you, ladies and gentlemen, please to keep your microphone muted until the time for questions and answers. You can send us your questions written if you want, and I'll ask Professor Feargal. And hopefully, I'm hoping that you enjoy the talk. And welcome, Professor Feargal, and I give the microphone to you. Thanks a lot.
Thank you very much, Ali. Yes, so I think what is really important here is that just to say a word about myself in terms of I started my engineering career in upstream oil and gas. So what I did was I worked in Aberdeen and offshore, but after that I worked for Shell and ended up running their non-destructive evaluation centre at University College London. After that, I moved to Cranfield University in Bedfordshire and was Director of Energy and Power there. Saw the light, saw what was happening with respect to energy overall and climate change and so on. And for the past number of years, I've been focusing on offshore wind in particular. So what I want to do today is I want to give a broad overview in terms of what the journey has been with respect to offshore wind, but also put that in the context of the overall energy transition. So what I'm going to do is just share my screen here and work through the presentation. Firstly, you know, it is my real a pleasure to talk today, and I'm very grateful to Ali and colleagues at the Al-Kindi Society, and very, very keen to share with you my view as to where this industry is going to go over the next 10, 20, 30 years. So in this presentation, I want to touch on these things. I'll start off with the energy and climate change context. Why are we doing this at all? Offshore wind in the UK and Europe today. And I'm focusing on UK and Europe because the UK has half of all the installed offshore wind power worldwide, and Europe has together, the UK and Europe, almost 96% of all the offshore wind. So it's something that started off in this part of the world. I'll explain to you why, but also how that is being rolled out, and in particular, the change of government in the USA. We're seeing big announcements on a daily basis with respect to this topic, and also in the Far East and other parts of the world. We've been involved in this for around about 20 years. We've been building wind turbines out at sea for about 20 years. We've learned a lot. This is pioneering stuff. So I'm going to talk about, obviously the successes, but some of the things that didn't quite work out. And I think it's important that as engineers, as a technical community, we learn from the stuff that doesn't work equally as much as the stuff that does work. I'll then talk about where are we going in terms of future projections and trends for offshore wind. I'll talk about structures, because it is the structure, the floaters and so on, which are the things that are primarily different to onshore, and then try and pull all these things together. So look, with respect to climate change, it's fairly indisputable as to what's happening to our climate. We see the extreme events, but I'm not a climate scientist, but I rely on the authority of the great majority of respected scientists around the world. Man has created this situation. We just happen to have too much CO2 in one part of the carbon cycle that at one particular time, and it's up to us to manage it. We have to manage this, and with respect to anything like this, the world looks to engineers to solve these issues, and that's why I'm always happy to talk to engineering communities about how are we together going to ensure that we have solutions so that future generations, our children, our children's children, and so on, will benefit from the kinds of things that we've been able to enjoy. Before really moving on, I think it's really important that we talk about energy and what is energy. And the way I like to present it is that we've got 4 pillars of energy. We've got affordability, sustainability, resilience, and reliability. And if we talk about affordability, firstly, we need, as we develop our societies, we cannot build any sort of developed society without affordable energy at a level that allows economic growth and maintaining our living standards. And affordability is really important. Yes, we can get energy from all sorts of different ways, but if only the very rich people can access this, then it's not any good, really. Sustainability, and I'm using the United Nations definition of sustainability here, and that's development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Hydrocarbons are a finite resource, absolutely wonderful resource. I'm pretty sure that easily in the future, it may not be 100 years time, but certainly in the future, teachers in school will tell children, they'll say, can you believe it? They used to burn this wonderful stuff when you can do so much other things with hydrocarbons. In terms of adding value to hydrocarbons, if you were to refine them, and if you were to feed hydrocarbons into the petrochemical industry, materials, pharmaceuticals, and so on, you can add an order of magnitude to the value of crude oil, for example. So, this should not be, when we talk about the energy green revolution, the hydrocarbon people should not see this as a threat. It should say, look, if you got sun, let's use the sun. If you got wind, let's use the wind. And if you got hydrocarbons, add value. You've got that responsibility to to society to ensure that you maximize the potential from this. We've got resilience and reliability. Resilience is of the system to cope with shocks and change. Um, and that's about having a balanced portfolio. So although I'm talking to you today about wind, it worries me that certainly in the UK, we're talking about putting a lot of eggs in the wind basket. And if we, surely if we've learned something from the last 100 years, is that we should have a diverse portfolio of where we get our energy from, so that we don't have to depend on any one source for our energy requirements. We all know only too well that that leads to conflicts, international conflicts, and so on. We should have learned from this. Reliability from our energy perspective is to rely upon energy services when required. I've done a lot of work in the west of Africa, for example, and if I'm in a meeting or giving a lecture, the lights are coming on and off, several times during that period. It's very, very difficult to develop something unless that energy is there when you need it. So it's not just about cost, it's about all of these other things. And as I talk about wind power, as I talk about other kinds of power, it's important that we understand these elements. In the UK, people spoke about, was wind energy cost competitive? Of course, no new industry is cost competitive. But as you get the economies of scale, but what you can also say within your overall system, you know what, you can afford to pay a little bit more for energy if it's in part of a portfolio which that means that you satisfy those total four pillars: the affordability, sustainability, resilience, and reliability. With respect to climate change, the predictions, generally speaking, and this slide is really to say there is no one unique solution. How do we get to control atmospheric CO2 values? Globally, increase nuclear power, solar, wind, wave, tidal, biofuels, fuel cell technologies, carbon sequestration, carbon capture, utilization, sequestration, domestic energy efficiency, industrial efficiency, reduction, all of these sort of things. Yeah. And the main purpose here is to try and say, we need everything. We need all of the above. And the correct solution or the ideal solution for the west of Scotland is likely to be different in terms of the mix for the southeast of England to, maybe coastal areas in the Middle East or inland areas. It depends on what resources are available. And that's what we have to try and understand. What we're all about here is having a portfolio or an armory of solutions that us engineers can provide to give that total effect. If we were to look at UK electricity generation, here it is in 2019, and I have moved subtly from energy to electricity. If I look in the Middle East, generally speaking, electricity, compared to transport, certainly in the UK as a total, about a third of our energy is electricity, about a third is transport, and about a third is heating. In Scotland, about half of our energy is heating, so about 25% is electricity. Globally, and we're closer to about 50% used for transport. But if I'm just to look at the UK electricity generation in 2019, around about just over 20% came from wind and solar. I have been showing this plot for the last 10 years. When I showed it first 10 years ago, that value was less than 2%. And we had, so in 2019, we had 1.8% of our electricity from coal. 10 years ago, that was 37% from coal. So when we talk about an energy revolution, and in terms of the UK's total 70 gigawatts of installed capacity, these are huge, huge numbers. And to go from something tiny up into 20% is quite extraordinary. With respect to where is that coming from? So today, you know, in the UK, we have wind, which is obviously we don't have the sun that we have in the Middle East. So wind is the predominant thing that that gives us this wonderful potential. Certainly recently, we've got around about 13.7 gigawatts installed onshore, but we've got over 10 gigawatts installed offshore. Onshore, we're not building anything new. We've a little island. We've used up all the good sites. We've got people complaining about wind turbines and farmers and whatever. They're not happy about seeing these things. Offshore makes far more sense. Anybody who's a keen sailor, or if you've gone offshore, you always get wind. You got much more reliable wind. If I take two identical wind turbines, put one on land and one offshore, I will get between 30 and 50% more power over the lifetime of that wind turbine offshore than onshore. Onshore, I've got trees and mountains and hills and also buildings and stuff in the way, and it's not so good. But roughly speaking, we've got, you know, today we've got over 18 million homes powered just from wind electricity. You know, so these are big numbers and set to grow even further. In terms of investment, offshore wind is the largest, certainly in Europe and now in the USA, is the largest single area for investment in the energy sector. This slide is a year old, so it's already showing where we are today, 2030 and 2050. But I think what is important is I want to talk a bit more about the macro side, because it's not just about the electricity or the power, it's the benefit to our societies as well. So this was showing 8 gigawatts of offshore capacity. We're now over 10. 2030, the plan was to have 30 gigawatts. And that has now been revised by government to 40 gigawatts. So today we have 10. It's taken us 20 years to get to 10. We have to, in the next 9 years, quadruple what we've already done as far as offshore wind is concerned, which is absolutely huge when you consider it. And by the time I'm finished my talk, you will understand that the numbers are eye-watering, and certainly the size of the structures and the investments are huge. And then by 2050, about 50 gigawatts of generation capacity. Remember, our total in the UK, of all our power stations and everything, are 70. And that's to run our trains or run our, you know, run all the industry and domestic. 70. By 2050, the plan in the UK is to have 50 gigawatts of offshore, not onshore, offshore wind. And with respect to that, we're talking about 40,000 skilled jobs. We're talking about an export of over £5 billion in exports. And that is from a country that doesn't even make wind turbines, okay? So, and I'll explain all of that to you of how we achieve that. When we look at electricity, we look at something called the levelized cost of energy, or the levelized cost of electricity. And what we mean by doing this is because renewables, whether they're solar or whether it is wind or other forms of renewables, tend to be capex intensive. So we put a lot of money into building the machines themselves. We don't pay for the sun, we don't pay for the wind. And so the OPEX, so unlike combined cycle gas, for example, you know, are over the life cycle, the biggest cost is the cost of the gas. But with respect to renewables, the biggest cost is the cost of the machines themselves and the plant and so on. So that's why what we take is a levelized cost of energy. And what we do is we take the total cost, so the capex plus the operational cost, and we put those together and we see over the lifetime. So over the 25-year lifetime of an offshore wind farm, for example, what is that? And what we have here is we have a comparison on the top, or alternative energy, and compared with conventional energy. And this is a comparison done by Lazard in 2018, and he updates these. One thing that you'll see on top, the green ones on top, huge variation in cost. If you look at solar PV rooftop residential, from $187 to $319, dollars, and that is in dollars per megawatt hour generated. If you solar panels are fine, but you put them in the wrong place. You know, if you put solar panels in Scotland, where I am, you know, it's quite expensive because you know the capital cost is the same, but you know we don't get the sun, and so it's not generating the megawatt hours. So you have that huge variability. The same with wind. You know, you got to put the stuff in the right place. If you don't have wind, don't put it there. Use something else, and that's why you have those scatter bands. The utility scale solar and utility scale wind, you know, much lower. It comes right down. So when you see wind at the bottom between $30 and $60 per megawatt hour, and that compares better than conventional, better than your combined cycle gas. The worst thing you could possibly do for the planet and for your bank balance is using diesel generation, and in many parts of the developing world, you know, these are used as backup systems. This is the worst place you want to be. So really interesting is what has happened, but you can see that the costs of these things, these technologies, is just a no-brainer, you know, to go for this. The learning curve, if you like, or the economies of scale, how has LCoE developed with respect to offshore wind in the UK? You could see back in 2017, we were paying 195 pounds, or sorry, this again is normalized back to US dollars per megawatt hour. And in, you know, a few short years, and where we are at the, you know, this has dropped dramatically. We were down to less than 70 pounds per, sorry, $70 per megawatt hour, just last year, and that's set to continue to decrease as we've gotten better confidence in the industry. We have learned a great deal. The economies of scale, the fabrication plants, the standards have improved, and so on. But also, investor confidence has been developed, and the biggest single element to this reduction in cost has been the cost of finance, because we now have mainstream investors like pension funds and so on, very happy to invest in offshore wind. The cost of finance before, when it was an early stage industry, it was more expensive to raise investment. Now investors are fighting over each other to try and invest in this area. Again, this is another comparison with respect to offshore wind compared to, you know, the usual suspects with respect to electricity generation. Now, this is something I'm going to spend just a little bit of time on, because this is a lesson I try to teach to UK government and so on, because very often I was in Brazil before the lockdown as part of a UK trade investment delegation, and the Brazilians are saying, well, you know, what's in this for us? You know, it's just going to be the Germans are going to supply, and the Siemens Gamesa's will sell the wind turbines, and the Vestas and Gs, we're not going to make any money out of it. And what I say is, that's where you're wrong. If I take the life cycle cost, the lifetime cost for a typical offshore wind farm, the turbine is, you know, the bit on top with its blades, and the Siemens Gamesa bit is 24% of the total project. If you look at development, the development costs are about 2%, but in terms of installation, so these are the local installation contractors, 12%. The balance of plant, you know, the offshore structure, the cables, the other bits, you know, 20%. And the huge element here is the operations and maintenance. And these tend to be people intensive, where we want to keep these things going, maintaining them. And these are the big area in terms of the overall cost, but also it means this is employment. And finally, we have decommissioning. So when we look at maybe the Siemens Gamesa bits, fine, that's fine. You know, it's difficult to compete with them at the moment. I'm not saying people necessarily want to do that, but you know, 76% of the total cost, of the total value, is the non-turbine bit. So this is still something very, very big. And this, when I talk about employment, I'm talking about macro benefits. This slide shows you in terms of the overall cost, but it also shows you the employment potential. Half a gigawatt, 500 megawatts, is about 2.1 million person days in terms of employment. And we often think of our coastal communities too in terms of being some of the most socially underprivileged and deprived, and that tends to be similar all around the world. And if you can provide local content, local employment, this is a good thing for the economy. You're using renewable energy. You're keeping your precious hydrocarbons for higher value co-products. This is all good news. So this is the European Union's scenarios. They've got a low scenario and a high scenario, and between that, they're looking at the huge amounts. 397 potential gigawatts of wind energy. Looking at it in terms of investments, these are huge amounts of money. Avoided CO2 emissions, but also enormous amounts of 750,000 people potentially employed in 2030 across Europe. Every graph I show you with respect to anything to do with renewables is exponential. The global wind capacity potentially set to rise to 520 gigawatts by 2050. This slide is, again, I think 18 months old, completely out of date. This is an underestimate, and I'm going to explain to you in a few minutes as to why we're only talking about electricity here. There's a lot more that we can get from renewables than just electricity. Changing names for a changing world. Our big energy companies are changing. Ørsted used to be called Dong Energy, which is the Danish oil and natural gas. Equinor, we used to know as Statoil, and they understand, they can see public perception. The public perception globally is, people, particularly younger people, want to see a cleaner, greener, more sustainable world. And I think, just looking at what is happening, that many of the big former oil and gas companies have rebranded, and they're looking to see themselves as in part of a general energy companies. When we look at stakeholders, I've spoken about the oil and gas companies, but in terms of general stakeholders, certainly here in Scotland or in the UK, I'll start from the top and I'll look at, we've got the Crown Estate, and the Crown Estate in Scotland. The Queen theoretically owns the seabed, and so the Crown Estate, she and her family want to make some money out of the seabed. And in the same way as with respect to exploitation of hydrocarbon reserves, major stakeholder. Developers and operators, obviously the big names, the big companies, the EDFs, the E.ONs, the Centricas, all of these. Investors and insurers. Certification authorities, so the Lloyds, the DNVGLs, the Bureau Veritases, the American Bureau of Shippings, all of those. Ourselves, our universities, research providers and training providers. The OEMs, the Siemens Gamesa's of this world, the Vestas, the GEs, fabricators and supply chain designers, government agencies. I've got health and safety executive and so on. You got non-government organizations, the RSPB, from birds and fishers, men, and all of these things. Port authorities, local government, training skills providers. So you can see that this is a big conversation we have to have. So it's not just a question of, us deciding let's put a wind farm out here. We've got to engage with, and this list is not exhaustive. It is stakeholders, the general public, we're all involved in this. And it is what's really important here. And sometimes as engineers or technologists, we don't see some of the softer things. And what we need to be able to do is engage with respect to not just the environmental impact, but it's the the perception of environmental impact, and the perception of other things as well. And so what we have to do also as people in universities and research providers and trainers is to train people and educate people as to, you know, what the implications for these developments are. So this is multidisciplinary. We've got the hard multidisciplinary engineering aspects, but also we have many of the other softer elements too that have to be taken together. I mentioned to you at the beginning, all hasn't been plain sailing, and it all hasn't been rosy. We've had a number of high-profile failures. I'm just putting a few up here from the media at the beginning. And when you consider this is a pioneering development, we've had, I'll just look at this one, for example. This is the first wind farm, US contractor Fleur, so a wind farm, Greater Gabbard in the UK. To cut a long story short, Fleur, it, you know, had to account for a $400 million hit on their accounts in one particular year due to a design and fabrication failure on one wind farm. So such as and what happened here was that you had grouts and transition pieces. The specification was wrong, DNVGL was wrong, but you can never get away with suing these guys, and they ended up in the High Court, and they were in London, and there was along with a string of other cases as well. But as we went through this, we learned a lot, and you know, what I would like to think is that having come through that learning, that's why the investor confidence is so much better now than it was 10 years ago. So, and what I would say is that we still have cases going on. We're still learning. If anybody is to try to tell you we have all the solutions and we know everything about offshore wind, we don't. And I'll explain a bit more about that soon as well. This is something that I think our audience will understand quite well. If I plot cost versus probability of failure, and if I take the black line here, I can spend a lot of money on something and over-design it, and it will never fail. But the reality is I can't spend that amount of money. I can't build an artificial island. It would just be too uneconomic. You know, I've got the maintenance costs, I've got insurance costs, I've got risk of failure. And at some place, we've got this sweet spot. We've got an optimal cost with respect to taking all of these things into account. And I want to talk about failure, and I want to talk about safety. We know from an oil and gas background, we've got a very, very well developed safety culture. And this is something I would like to think that maybe sometimes people in the UK think we're a little bit over the top on these things. I think it's really, really important. I don't think we are at all. G+, which are all the operators operating in the UK area in offshore wind. And it is responsible for self-regulation of safety. And what I have done and what I continue to do is keep a tracker. And I plot this tracker, and I'm showing a comparison in yellow here of the total recordable injury rates per 1 million hours work, and comparing this with upstream oil and gas. And what you can see with respect to wind is unacceptable. It's been tolerated to some extent because the government and regulator has wanted not to over-regulate this emerging industry, but we are in a place now where we have to learn. We have to learn from our colleagues in offshore oil and gas. We have to learn from other industries, because the public will not accept these continuing high levels of incidents. As a direct result of our work here at Strathclyde, the UK Health and Safety Executive has written to all offshore operators and told them that from this month, January 2021, they're visiting them all, and they will all be inspected on a regular basis. So what that is cost, but not at the cost of human lives. That cannot be tolerate it. The development of this, we show a Boeing 747 here of 76 meters long. These are the sizes we're getting to. Basically, we've got the largest moving structures on the planet, our offshore wind turbines. And when I talk about, half a gigawatt, when we start to look at 10 gigawatt machines, you're talking about 50 of these enormous machines. I used to give the example of a 5 megawatt machine of being the same as the London Eye on top of the Gherkin in London, and that was one machine. And when I explained that we've got 5,000 of those operating in the southern North Sea today, I'm now completely out of date, because we're now up to 12 megawatts machines, and we can see these. So we've got blade diameters going up to 200 meters. And which is quite extraordinary when one considers it. This is what has happened with respect to as we moved offshore. We started off with Big Ben on one side and the Eiffel Tower on the other, and we are fast approaching the size of the Eiffel Tower, as you will start to see in a minute when I show you the new GE machine. With respect to the majority of supporting structures, the great majority of them are what we call monopiles. I'll talk about monopiles, jackets, and floaters. Very, very few of the others, but we are where we are. If I'm to give this presentation again in 10 years' time, this is going to look very different. The blue area will be floaters, and we'll have relatively few as a proportion of monopiles, and I'll explain that to you. So for relatively shallow waters, up to 30, 35 meters or so, we can get away with these monopiles. We then move to jacket structures that are similar to small offshore oil and gas platforms. But once we get, and we show, or Atkins are showing 50 meters here, 50 meters, you're pushing it a bit. It's, I would say 70, 75 meters water depth, and you have to float, otherwise it gets too expensive. And then as you get deeper, you can go into spar type floaters as well. The majority of the world is, in terms of our oceans and seas, are deeper than 50 or 75 meters. So what has happened is that we've had unusually shallow water. We've around Europe, Northern Europe, southern North Sea, and this is how the monopiles have developed. This is what I was talking about a second ago, the Halonade X, the 12 megawatt, and this is, as I said, we're getting close to the size of the Eiffel Tower. One single machine, a 12 megawatt machine, and that is a commercial machine. It's not a test machine, it's a commercial machine. So when you consider that as on scale, you appreciate the enormity of these engineering tasks. And a few of the statistics here, so that people can, if they're interested, come back and look at these slides as reference. Just some nice pictures. This is the Belgian North Sea. These are some jackets. There aren't too many of them, but these are some jackets ready, loaded onto a barge, ready for deployment off Bremerhaven. This is how we fabricate the monopiles. They start off as sheet plates. We bend them, we roll them, we then stitch these cylinders together in circumferential welds. The big difference between this and oil and gas and ship structures are the wall thicknesses. And so we're going up to almost nuclear power size thicknesses, 100 to 150, 180 millimeters wall thickness. The thickest steel you'd see in an offshore oil and gas platform is maybe 32 mil. Most of it is about 25. And again, ship structure about 25, about an inch thick. These are several inches so thick. So this is quite different. I spoke to you about this is our water depths, and I said to you at the beginning, why is the UK, why has Denmark and Northern Germany got the majority of the world's offshore wind today? And it's all to do with water depth. The red area here is shallow water depth. I can go from the southeast of England over to Denmark, down to Germany, over to Holland and France, and I'm not going to get any deeper than 35, 40 meters. I also have enormous centers of demand. I've got northern Germany demanding electricity. I've got the whole London area that London Array is feeding in huge, huge demand. So I've got this perfect situation. I've got a lot of demand for electricity. Electricity doesn't like to be transported over large distances. And so if I have my power generation in relative close proximity to the demand, that's a good thing. I've got very sandy, chalky soils. I can bang these monopiles in relatively easy. And so what we've essentially done is we have de-risked. We have literally taken onshore wind and literally dipped our toe in the water, made sure that worked, got a little bit deeper, and we de-risked. And that's why. That's absolutely the only reason why offshore wind is the success it is today compared to wave and tidal, for example. With wave and tidal, you don't have that intermediate de-risking step. You know, it's all or nothing. With respect to wind, we were able to do this. The rest of the world doesn't look like this necessarily. If you look in the Mediterranean, you know, you go 200 meters from the shore, you're in 100 meters water depth. You're floating. Most of the Mediterranean countries there have to float if they're to develop substantial wind, and that's also where I am up in Scotland. Yes, we've got a lot of wind, but we're deeper. And floating is what we're working on all the time at the moment. We go to the USA, and even before the recent election, huge amounts. Certainly, if we start to look at Northeast USA, New York State, Massachusetts, and so on, huge amounts of offshore wind in relatively shallow, and a little bit deeper than the southern North Sea. But then they have much deeper areas. You go to the West Coast USA, you got to float. It's deep. Now we've got the new administration in the USA, and you know the announcements that we've heard ever since Mr. Biden's inauguration has been he's doubled the funding for offshore wind. Every day there are new announcements, and this is certainly an exciting market to follow. Floating, I've been working up to this. Not too far away from me here is the world's first floating spars in Peterhead, built and operated by Equinor, formerly Statoil, mainly using oil and gas technologies. But these 6 megawatt floating spars have been continually generating electricity now for over 3 years, and have been a wonderful success in demonstrating what can be achieved. We've had the US firm Windfloat. This is operating off the Portuguese coast, and that has been operating as a demonstrator, as a semi-sub type technology. Quite nice. It's got an adaptive motion suppression system. They're pumping water around depending on the wave environment to stabilize it, and that's been working quite nicely. People talk about floating and they say it's more difficult to float, but there's tremendous opportunities. We can do things completely differently if we float rather than fixed. And the opportunities associated with these are, we can remove humans entirely from offshore installation operations and maintenance. So offshore, so what we can do is we can make these machines close to shore, close to in coastal areas, and then we float them out as integral pieces. So we're not, putting people out in the middle of the sea and trying to do these 100-meter lifts and having people hanging out of cranes and trying to do up bolts high in the sky. So floating allows us to do this. And for maintenance, these floaters can come back. We can come back and swap out components like we do with aircraft. We'll swap around gas turbine engines and so on. We wouldn't dream of trying to do that in the sky. So with floaters, we can do something similar. Integral unit deployment can significantly avoid offshore site assembly, high lifts, etc., making all year round installation possible. Reversible moorings can mean major interventions and retrofits can be conducted in coastal or near shore. And floating and mooring systems can be designed to have a significant damage tolerance. And really importantly, there is no upper deep water limit. I can float equally, I can have the same floater in 150 meters as in 3,000 meters. Okay, I might need some longer moorings, but you know, the technology works. The other thing that we're starting to see a lot more of are floating multi-purpose platforms, and that is combining energy production with food production, for example. And here is an illustration of an aquaculture, so fish farms with offshore wind working together, and potentially support for transportation and other things as well. This is an example of some of the research we're doing with the European community, developing and demonstrating this multi-mode platform. This is some research that we have done some years ago. 10 years ago, we had a large project with the Energy Technologies Institute. We looked at vertical axis floating wind. And the conclusion from that at the time was vertical axis really comes into its own when you start to float, because you've got a lower overturning moment. It doesn't try to topple over your floater as much, but also it is independent of size. So with vertical axis, it doesn't matter how big you make it, it doesn't increase the stresses on the structure. With horizontal axis, you know, the bigger you make it, the heavier it gets, so the stresses get larger. So vertical axis, we will see in, you know, 10, 15, 20 years time, we're going to see these kinds of things mixed up with horizontal axis as well. The aerodynamicists, and maybe we've got some people with aerodynamic background here in the audience. The pure aerodynamicists 10 years ago would have said, oh my God, you know, you couldn't have aero structures in close proximity to each other. Vestas have now started to research how to put multiple turbines on one particular supporting structure. And here we have a development that is showing one floating platform supporting more than one wind turbine. So these are the types of areas that we're going to see more and more of. These are some colleagues in Holland, in Maren, and they're looking at very, very large floating mats, if you like, articulated mats whereby we can put wave and wind power facilities on them, and indeed floating solar as well. And if we are operating in a part of the world where we happen to have good sun, why not? Curtailment is important. In the first few months of COVID in the UK, we experienced a huge reduction in power demand, and it cost £500 million for the government to pay back to the wind operators not to generate electricity. So this brings us to, you know, what happens when we produce too much power, and then when the wind doesn't blow and the sun doesn't shine, you know, what do we do in between? You know, we're not generating anything. So the whole aspect of storage is the elephant in the room. And this cuts across all renewable energy. You know, if I don't have the reliability of knowing I've got fuel that I can burn when I want it, I'm waiting for Mother Nature to give me wind or give me sun. It is not so predictable always. And this is where we start to move into green and blue hydrogen. This is the hottest topic around. This is a serious report. I've given the reference to it if anybody's interested. And that is towards net zero technical report on green and blue hydrogen. Green hydrogen is taking renewable electricity and instead of feeding it into the grid, you know, making hydrogen out of it. So hydrogen can be converted to ammonia. Ammonia can power ships, and also the hydrogen can be stored and then used to generate electricity when the wind isn't blowing. Blue hydrogen is the hydrogen along with methane from the gas production, natural gas production, and that is feeding the hydrogen economy rather than natural gas, hydrocarbon. And with respect to a non-grid connected system, so I said to you earlier that all the predictions on offshore wind only feed into necessarily electricity. Offshore wind solar, renewables in general, power to X, power to electricity, power to hydrogen, for example, means that it changes the whole dynamic of where the world is going to go. Certainly in my lifetime, I'm not going to be on a commercial electrical commercial aircraft. I will be on a hydrogen powered aircraft, and I know that. We've tried biofuels. There are issues associated with biofuels, competing with food, with agriculture, and so on. That doesn't work so well. Hydrogen is a no-brainer. This is a project we did with the EU some years ago, and that was wind to hydrogen, and also we've got aquaculture supported in there as well. I put this up in terms of low carbon shipping. A lot of what we do as well in Strathclyde in terms of the department, shipping accounts for something like between 4 and 6% of global warming greenhouse gases. There is a real potential here also to reduce our carbon footprint significantly within marine transport. Aerospace is more difficult. Rail is easier in terms of electricity, but in terms of transport, shipping is a big one. So the industrial strategy for us is to have 40 gigawatts by 2030. 60% local content. To date, the UK has been importing a lot of the content from our continental European friends. We can't afford to keep doing that. We have to increase the macro element. So there's a lot of interest in how do we design these things? How do we fabricate these things, maximizing local content? And as engineers, I say to people I've got a department where I've probably got about 30 naval architects who can give me another 30 different ways of floating a wind turbine. And if they were told that you want to make this so that the fabricator down the road who's been hit by COVID, who used to make cars, and no longer that industry is working so well, how can they shift? How can they retrain? How can they repurpose so that they're supplying this hugely growing market? And also in terms of diversity, a third female, this is not about just ticking a box saying that this is equal. This is about attracting the brightest and the best people. We can't rule anybody out in terms of ethnicity or gender or age or whatever. We need the best people from wherever they come from in order to develop this hugely exciting application. Standards are really important, and I'm quite sure there's some people who are involved in different industries listening. Prescriptive-based standards are fine, but prescriptive-based standards where you detail every little thing tends to reduce the pool of suppliers who can supply into a particular market. And it limits innovation. If we have goal or competency-based standards where we have highly educated people who understand the functional requirements, but who are free to come up with different innovations and different ways of achieving those, then that means we can expand local content through expansion of the supply chain. And what that means in terms of the training element is to train our engineers and our economics and project management people to better understand what might be possible rather than following a prescriptive rule book. Just some links to the EU Blue Growth Strategy. This is all about maximizing the potential from our oceans and seas. So to summarize and conclude, offshore wind has been a phenomenal success in Europe to date in terms of cost competitiveness and scalability. However, safety needs to be urgently addressed at every level. Safety by design, rather than looking at safety as an afterthought, work ultimately towards human-free autonomous installation, operation, and maintenance. Marine robotics, structural health monitoring, condition monitoring, all of these things. Our instrumentation engineers looking at wireless ways and human-free or contactless ways of communicating with these structures all of these things, even if you're not particularly interested in a wind turbine itself, there's huge opportunities within these related areas. The next decade will bring larger floating deeper water platforms with shallower water deployments and maintenance. New turbine technologies will continue to be introduced, including multiple rotors, optimal farm configurations, and then getting onto the hydrogen. The first non-grid connected far offshore liquid fuel generating plants will be demonstrated very, very soon. And I guarantee you, we're going to see a lot more in this area. And I guarantee you will see these demonstrations in the next 2 years. They're already under development. Intermittency of renewable energy resource reminds us of the requirement for, do you remember when I spoke about the 4 pillars of energy? I'm talking about resilience and having that balanced portfolio. So wind is not the silver bullet. It's not our answer to everything. We need everything. We need what we can. It's also not just about energy, power, whether it's solar power or wind directly into desalination, into other applications, is a tremendous potentially growth area. The future, as far as offshore wind is concerned, the floating structures, safety, standards and guidance fit for the local supply base, non-grid connected offshore liquid fuel generating plant. And that's what I say is the resilient system. So there we go. 3 of them: safety, standards, and future systems. Thank you very much.
Thank you very much, Professor Feargal. What a journey you've taken us. It's educational, interesting, learned of course, technology, science, update, future, environment, all within an hour. Thank you very much. Much appreciated. I'm sure the audience, they loved what you've told us so far. But I've got some questions for you and some interesting questions as well.
Right.
I start with one question, the first questioner, which he asked, I think is to do as well with the environment in the Middle East. Is what is the minimum speed for a wind turbine to generate an efficient and successful power? And why why don't we use the 10 and 20 kilowatt at home installation to reduce the cost of power transmission? And this comes to I think those 2 questions come to the first one as well, is to tackle the lack of infrastructure. Therefore, at home you put a power with the wind in that specific area region, and what is the minimum? Would that be useful? Then I don't depend on the government to give me the line. And the other one, which wind around my area will be enough for me to install wind turbine?
Okay, great questions here. So let me start off with firstly, so wind, we know wind is a variable speed. So the first question was, what's the minimum? We generally talk about, with respect to these size of wind turbines, and I'll talk about different sizes in a minute. But generally speaking, we talk about less than 4 meters per second wind. Not a great deal is going to happen. We talk about kicking in around about 4 meters per second. Our rated wind speed, and that's where you have the rated power. So if you said you had a 500 kilowatt or a 5 megawatt or a 10 megawatt machine, it's generating 10 megawatts at that rated power. And that rated power tends to be 11 or 12 meters per second wind. It will carry on to generating electricity up until you cut it out. And you generally want to cut this out before the wind gets too strong and causes structural damage, causes damage to itself. Yeah? So we generally will cut it out around about 20 meters per second, given that we'll have gusts going up to about 24 meters per second. So if we start, so you imagine we're starting at 4 all the way up to about 24-ish, and we're generating power at different amounts depending on the wind speed. And the wind, don't forget, the wind is moving about, it's gusting, and so on. So, but that's the general envelope. We'll design against a hurricane extreme event. Maybe that can be, in extreme cases, 70 meters per second. So we're going to design that, but the turbine itself will be in a locked down. It will be in a survival mode. So that's the sort of range we have. If I was to say that in parts of Scotland, offshore, we've got average wind speeds of about 12, 13 meters per second. There's you don't get anywhere like that anywhere in the world. If I go over to China, I didn't speak so much about China, the Chinese offshore wind. It's very, very different. They don't have great wind resources necessarily. Up north, they tend to be down at average wind speeds of about 6 or 7 meters per second, and down south they tend to go up to about 9-ish, which isn't wonderful, but our friends in China tend to get around this by just making more of them. I think the question about the local area of this is very important. I was taught a great lesson some years ago when I was at Cranfield. We were approached by Keppel in Singapore, and that was to test a tidal energy device. And we tested this. We did a techno-economic environmental impact assessment on their proposed device, and we put it in a tank, and we did the tests and so on, and we gave them back the results. And we said to them, it's okay, it looks okay, it looks fine, looks like you can engineer it, you can make it work, and it will produce. And at the time, it was a 1 megawatt machine. And we said, but our concern is how it will work alongside other machines. Will we have, because a characteristic of this was that it used to disrupt the flow quite a bit, so that the adjacent machine would have dirty water, if you like, or dirty current, rather than a nice clean current coming at it, and similar to interaction or wake effects for wind. And they said, no, we're not interested in arrays. We just want one single 1 megawatt machine. And we said, well, nobody's going to be interested in that. And they said, here's a lesson for you, Professor. The rest of the world is not like grid-connected UK and USA. Their market were the Philippine Islands. There were remote communities that they had good tidal currents between the islands. And 1 megawatt was very, very happy. They're very happy for a community of 20 or 30 families, for example. And with tidal, you always know where the tides are going to flow. So much more predictable than wind. And so my lesson was learned very much, and I'm glad to be able to share that with you as well. Is that in many parts of the world, and certainly I'm now that I'm in Scotland too, we got remote communities in remote parts too. We got islands, and the potential for generating relatively small machines, being able to do these, this works quite well. What I will say is, what do you do when the wind doesn't blow? And that is the issue with the remote one. You can have big battery systems. But also increasingly we're starting to see, as I say, smaller compact units that will generate hydrogen and ammonia for storage, so that this satisfies your storage requirement as well.
Thank you very much, Professor. Professor, there are a few questions, but I don't want to leave this a question without asking you this question. Where do you see, from what you know so far, the capability of the Middle East, a country like Iraq, like the Gulf states, their financial and even first environmental capability, wind speed, and where do you see the wind energy sector in the Middle East and in Iraq, for example, from what you know? I don't know how much in depth you know the countries in details, but from what you know, from the literature, from what people are talking about? Yeah.
Well, this is very much in terms of, you know, you tend to, as you get more closer to the equator and so on, you know, as you tend to, the places where you have a lot of sun, you tend to have less wind. Obviously, with respect to Iraq, you know, you do, and as you go further north, you know, you get into more mountainous areas and so on. So the country itself is large, but it also has some very differing uh, environmental characteristics, and that's why I say is that, you know, you use the resource you have that makes sense. Um, I, I got involved in looking at a situation in Africa where wind turbines were sold by a European manufacturer into Africa, and those wind turbines had been optimized for the high wind rates that you get in Northern Europe, and they shouldn't have sold them into Africa because the efficiencies of these things were completely wrong. There is the potential to optimize in terms of wind turbines for lower wind speeds. Um, Offshore, as I say, typically you tend to get more more um, predictable wind, and particularly, you know, no matter where you go around the world, you will always get reasonably good wind at some point during the day, due to, you know, your Meltemi or your sea breeze, and so on. So there is potential, but what I would say is that every site needs to be characterized and looked at carefully, and you know, that what we have to do is to use a combination of the resources which are available. What I would say too is that I mentioned floating solar, and multimodal power plants. So we're also seeing combined floating wind with solar as well, and we're seeing those kinds of developments too. So you know, this is why education is really important, and training is to understand and characterize the resource, you know, but also to understand the different sorts of technologies that can benefit that from that resource, and you know, the correct solution, or the optimal solution in, you know, the Persian Gulf, you know, is likely to be different to land-based, but also other areas, maritime areas as well.
Thank you, Professor. I've got a question, but it's multi-questions in the same time, one embedded inside another. The first one, to go to high power wind turbine plants like 30, 50 gigawatt, how do you address the fluctuation in the wind energy when you go to such high demand and high power? That is one, please, if you can mark it. Number two, as you saw in one of your slides, the OPEX cost is quite high, about 40%. Or how can we address this from the competitiveness issue with energy? And I'll come to the third one after you address the 1 and 2, please.
Okay, so let me address the second one first in terms of the OPEX. That the OPEX, that's relative. So that graph is the OPEX doesn't have to be that big, but it's just showing that the OPEX is relatively large compared to the overall cost. The reason why it's expensive at the moment is because it involves sending people offshore. Everything we do offshore is an order of magnitude. It's at least 10 times more expensive than the equivalent operation onshore. And what I would say is that if we, you know, what we need to be doing, you know, in terms of the UK banned commercial diving in offshore oil and gas, and I think it was in 1992. The Norwegians, I think it was 1988. And ever since that, routinely, we use marine robotics, we use ROVs, AUVs to intervene. So we're not putting people offshore into those hazardous areas. So, you know, by sorting out the safety issue, we will also ensure that we'll reduce the OPEX, because, you know, sending people, we're better off employing engineers to make the robots that repair these things, not sending people outside. And then that also gives us the high value, the highly technical skills required, rather than guys who can just climb up a ladder with a toolbox on their backs. With respect to the first question, in terms of the variability of the wind coming in, this is the big challenge, huge challenge, and that's what I say is the elephant in the room, the storage element. So on one hand, we've got curtailment, the network, electricity network, saying stop producing this. We've got nowhere to use it. And if you stop doing it, we will still pay you for producing it, but you're not producing it, so we're paying you for producing nothing, and that's not a good idea. And then the other thing too is then when the wind isn't blowing or the sun isn't shining, what do we do with respect to that? And that's why we need this additional vector, this energy vector. And with respect to storage, typically, or depending on where you are, you know, if you are located in an area with close to some mountains, that's nice, because you can build a pipe and you can pump water up the mountain when you've got too much power, and then when you don't have any power, you can let it down, and that can generate some electricity through a turbine. We know this stuff. It tends to be quite expensive, but we know how to do this, and that's. However, in many parts of the world, we don't have mountains, and it's not economic to pump store all of this, and that's why the hydrogen is such an obvious advantage. We can use hydrogen compatible with many of the natural gas appliances and infrastructure. We can use natural gas pipelines. We can use hydrogen in those. Even for boilers and other things, we can replace with hydrogen. The German government has already started to dose its natural gas with hydrogen, and that's why hydrogen and ammonia, for example, ammonia is less volatile and better suited to storage. And so I think, also, the wonderful thing about oil and gas has been the flexibility of it. With oil and gas, if you've got a tank full of this stuff, you can send it somewhere, it's going to be there, you can use it immediately. And that's with electricity, unless batteries themselves, we have seen smart grid networks, the idea that we're all going to be, our Teslas are going to be plugged into in at nighttime, and they will be, all of our Teslas will be used as a big storage. Maybe that sounds nice in some very, very developed parts of the world, but for the vast majority of the world, that is not realistic. And that's why I say that what do we do when to deal with the variability or intermittency of electricity is we need to be able to put that electricity into another energy vector, whether it's some form of storage, whether it's a battery, whether it's water, whether it's hydrogen. We need to put it somewhere, otherwise we're wasting it.
Thank you very much. The third question, I think you touched on it, is to do with the amount and number of incidents, which you said, I think, because it's a remote area, but please feel free to touch on it. But one of the sub-questions as well is saying, why don't we use the infrastructure from the oil and gas industry, like jackets, used jackets to erect and put turbines?
Yeah.
But there is another question. I think I'm trying to connect the questions together so that you answer them all in one go. It's the sizes of the vessels for decommissioning. Mm-hmm. So when you come to, are there enough out there, especially for the North Sea? And what are the decommissioning challenges? Yeah, thank you.
Sure. Okay, so firstly, in terms of using offshore oil and gas infrastructure, before I go into that, in terms of why do we have such safety incidents? Firstly, if I am to design a power station, I wouldn't start from saying I'm going to put that power station 100 kilometers from shore, and then once you get onto it, I've got to jump from a boat onto this thing, and then I've got to climb up with a toolbox 100 meters above the seabed. So as a starter, this is not a good place to start to build my power station, but this is what we're doing. And this is what wind is, where you go up high and we're going offshore. So you can guess pretty well why we have such safety incidents. Even getting somebody from a boat, and you can go on YouTube and you can watch the videos and you can see what they call crew transfer vessels. And the crew transfer vessels, they're there, they're waiting for it, and they'll jump across onto a ladder. This is not safety by design. As an engineer starting off, you don't want to do this. You wouldn't, if you were designing a railway system, you're not going to design a railway that continues to go around at the same speed and have people try and jump on and jump off. That's going to be a dangerous situation. So the other thing is the installation. You're trying to assemble all of these things offshore, and the wind is blowing, and you're putting them in windy areas, and in areas that you tend to have quite hostile waters. So that's where the safety comes from. And what we need to do is to use our engineering ingenuity, just design the person out of that. We shouldn't be putting people offshore. It's a bit like wars or whatever. Governments should not be sending people to war. It should be a complete last resort. The same thing, you should not be putting people into a working environment that is a hostile environment. We've got our robotics, we can do that. Offshore oil and gas infrastructure, why aren't we using that? In 50 years of North Sea oil and gas, we have built 270 something platforms. We have now over 5,000 operating offshore wind turbines. The reality is that we need its volume. And so, yes, even if we did use all our decommissioned oil and gas platforms, even within the Gulf, if we stuck a wind turbine on top of each of them, we don't have the economies of scale. We don't have enough of them. They're not in the right area, in the right location. So we could try and do this, but it wouldn't be an optimal configuration. Wouldn't be an optimal system at all. What we can do is we can use the electrification system. So within the Gulf, within the North Sea, we have an electrical network. We've got networks of pipes and so on as well. They can be repurposed. They can be reused quite nicely. So a lot of the infrastructure, the port infrastructure, the support services, the crew transfer vessels, all of these things, these can be repurposed and reused. And really importantly, skills. So where you have a maritime community where you've got a lot of skills that are people who are used to providing support to marine energy, then this is all possible. With respect to decommissioning, I think the third question on that, we haven't decommissioned a whole lot yet, but we're not very far away from it. I spoke yesterday at a decommissioning event, and I suppose the difference is the few installations that we've decommissioned to date have been mainly for research facilities, research turbines, or very, very early ones. And they have been decommissioned as a one-off, so hugely inefficient, throwing lots of oil and gas jackups and semi-subs and things, large crane vessels at them. There is huge potential here that as the first generation wind turbines need to come out of service, and then we're replacing these with these much larger machines and newer technologies, we will be decommissioning hundreds of these every year. So there's two aspects to this. The way in which you decommission 100 compared to a one-off, you've got to rethink this. And certainly, I'm quite sure that we're going to see special purpose decommissioning vessels that will come in and hug the things and pull them out. I suppose the biggest question is, what happens in terms of the circular economy, in terms of the materials and so on that we use? At the moment, when you can imagine the amount of onshore wind, and we have glass fiber, significant amounts used in the blades. These currently are going into landfill, which is shocking. It's terrible. And one of the big challenges, some of the research areas my colleagues in Strathclyde and other universities are looking at is, how do we build plastics and glass fiber materials so that they can be reused, repurposed, recycled, and so on. So this is a huge challenge in terms of what do we do with all this good material when it comes to end of life.
Thank you very much. Actually, this leads me to another question: is what is the you answered the wind variation. I think you've given enough answers to the environmental impact on wildlife, and how can it be addressed around it. That is one. And another one will jump a little bit technical, I think. Why in solar energy, for example, and in the Middle East, one of the issue is the dust, and this accumulate on the solar cells. Yeah. The question is, for the wind turbine, what are the challenges? Technical, we touched on the cost, we touched on the wind variation, but on the science and engineering side, materials, stresses, that type, what are the technical challenges for wind turbines? So first, the wildlife, and second, the technical, scientific, engineering challenges.
Excellent. Okay, so with respect to wildlife, so we get wildlife above the sea and the air, tend to be birds, and then we tend to get them below the sea surface, tend to be marine mammals, fish, and so on. The issues subsea are different, as you can imagine, and those issues tend to be around installation. One of the challenges with monopiles is these big piles, they tend to be very noisy as you bang them in. And a lot of work has been done in terms of the effects on marine mammals and fish stocks with respect to the installation processes. Jackets have been, in some cases, jackets have been installed in some areas where the piles are smaller, much smaller, similar to oil and gas size piles. So you've got piles less than 1 meter in diameter, as opposed to some of the diameters we're going up to now in the monopiles are 10 and 12 meter diameters that we're banging in. So considerations have to be taken into account. There's a lot of research going on also around cables, buried cables, with respect to electromagnetic influence on marine mammals and fish and so on. If I was to say that there is, there's no such thing as having no impact. Of course, there's an impact. It's a question of being able to manage that impact and what's an acceptable amount of impact for the longer term. In the longer term, and I'm still below the sea at the moment, is that there tends to be some benefits to the wildlife beneath the sea. It tends to be because we make an exclusion zone around these installations, so we prevent fishermen from going in. Well, just because we tell the fishermen not to go there doesn't mean they don't go there. But anyway, they are exclusion zones, so the fish tend to have a protected area there, and also subsea that you have various organisms and so on, and you have artificial reef type benefits. I think one of the big challenges is with decommissioning, the same as we were getting in oil and gas, is, is it better just to leave them there, or parts of the structures there, or dig them out and pull them out? But unlike oil and gas, we don't have drill cuttings and so on that may be toxic. Over the sea, with respect to birds, many years ago there was a big concern about wind turbines affecting birds and migration patterns and so on. There tends not to be so much. The evidence is that birds themselves are smarter than people have given them credit for, and they know how to go around them. The challenge is that if you start to increase, and as I say, we've got 5,000 of these in the southern North Sea, and as we start to put more and more in there, there is the concern about them affecting migration patterns and so on. And these are considered carefully. To some extent, we're not there yet. We don't have the density or the volumes yet, but we're not far away. So, these are very important issues. With respect to the technical challenges, like where do I start? We're working offshore to begin with corrosion. All of the wind turbines that were built before 2015 were not painted on the inside. They were not protected, so they're all freely corroding from the inside out. I think I'd said in my bio, I think I'd spent 6 months between the High Court in London and the London Court of International Arbitration as an expert witness on a variety of cases. When the judge asked me, the High Court judge said, "Well, what would you have done, Professor?" And I said, "Your Honor, I would have painted the things." But he said, "Oh, the benefit of hindsight." I said, "No, if you go into the sea, you should do this." They were trying to save some money, so they didn't do this. They thought that this was a sealed compartment and would use up all the oxygen. But anybody who's involved in maintenance, that the maintenance guy is going to leave the hatch open and the oxygen will get in, of course. Yeah. Anyway, so that's happening. So with respect to corrosion, huge challenges with corrosion, deterioration of coatings, damaged coatings due to collisions, unforeseen events, and so on. So these are challenges. With respect to blades, we get abrasion. So we get these salt air has salt in close proximity. So the leading edge of the blades tend to get eroded very, very severely. So you have them going around in wet conditions with salt water, and so we get significant abrasion. A lot of interest in terms of we're now developing drones and so on to visually inspect them, and obviously to replace a blade is not a trivial task. In the early stages, there were a lot of issues associated with gearboxes and things. And what it was mainly about was that the engineers were trying to save weight on the top, because the heavier you make the thing on the top, the more is a challenge from a structural dynamic perspective. So they were squeezing back on the material, on the rigidity, I think, of the drivetrain platform support. And what that meant was that you got flexing and you had a lot of issues with gearboxes. Generally speaking, these have been designed out. But what we have at the moment is we've got a lack of reliability. At the moment, we are visiting on average each of the 5,000 operating wind turbines on average 14 times a year. And that's not good. And so what we need to be able to do is we need to be able to design them, put them out there for 5 years, for example, and like if we have a floater, pull them back, swap out your nacelle and your blades, and push them back out again and see them again in another 5 or 7 years. These are the challenges. But putting these huge structures in an offshore hostile environment, as I've said a few minutes ago, if anybody tells you that we've solved all of these challenges, they're not being truthful. I'm learning on the job every day, and so are our colleagues, and that's why we need more, top quality scientists and engineers. We need our brightest and our best. We need to attract our best younger people into the area so that we can solve these challenges.
Thank you very much, Professor. Professor, I promise you when we started, the time slot is an hour and a half. It's an hour and a half now, but I've got just one simple last question for you. I know it's difficult, especially when I cannot offer for you a cup of tea or water to that effect. Why throughout your slides we've never seen blades in parallel or in serial, one after another? I think they meant why one not behind another, that type of design. I hope that is an easy and a quick question.
Yeah, I think there's a lot of scope for this development. Don't forget, this industry is at its infancy, and we've far from optimized these. So the theoretical people, the aerodynamicists, want to have a clean, uniform wind stream coming at it, and they can predict them. I'm quite sure that in the future, like a gas turbine, not all the blades will look like each other. So you can imagine a wind flowing through a wind farm. The machines in the middle are seeing very different air than the machines on the outside. So I will guarantee you in 20, 30 years time, you know, you'll have some machines up here, some down here, some doing this, some doing that, and you'll have them mixed up. But at the moment, you know, we've not optimized multiple machines or arrays, and you know, there are decades, if not centuries, of further research for our aerodynamic colleagues and our material scientists and power electronic engineers and structural engineers. Plenty of challenges here to improve, carry on to improve this situation.
Thank you very much, Professor. Professor, I think on the behalf of Al-Kindi Society, I'd like to thank you for your time and your presentation. It's been so informative, so educational, and much appreciated. And ladies and gentlemen, I hope you enjoyed it as well. It's the beginning of, I hope, first step of collaboration and work with Professor Feargal, because he's got a lot of other areas that he will give us and enlighten us with his areas of expertise. So thank you very much to everyone for his time and her time, and hopefully we see you soon in another presentation. Thanks a lot.
It's great. It's my pleasure. Thank you.
Thank you.